As I've told you, see, just consider again that for metals we have on extreme left it is metal. So when we are moving, see, the example is already here, the alkali metal group. As we are moving down, what happens? The size is increasing, nuclear charge again decreasing. So that means the last one, metal, has a tendency to lose electron easily. That means it has the lowest ionization energy. So, and the element which has lowest ionization energy is considered as most metallic. So that means when we are going down the group, size increasing, nuclear charge decreasing, so obviously the metallic character is increasing. So whenever there is an increase in size, so that means ionization energy is decreasing, and the one which has lowest ionization energy is the most metallic. It can lose the electron more easily, and the more easily it can lose the character, that means it is a typical metal. So metallic character increase down the group. And when we are taking an example of the period, so what we see when I take an example, suppose I am writing the third period for you, what do you get to see in it? What do you see in it? That as we move down, I think there is no need to write the configuration because you are already familiar with it, how to write it and how nuclear charge is decreasing and how the size is increasing as we did in the previous property, but still I am writing it for you to get, so that you should be well versed with the concept. So as we are moving, that means it has the biggest size, right? Biggest size means out of them it has the lowest ionization energy, right? And out of them it has the, I'm just excluding the noble gases. As I've told you, they have stable noble gas configuration, so we won't be considering it. So I'm taking example till halogen group. So chlorine is the, you can say, the smallest one out of this period, and that means it has got the maximum ionization energy. So that means if we want to remove this electron, less energy will be required, and less energy required means that it can lose the electron more easily. More easily the element lose the electron, more metallic it is. So that means it is metallic. But as we are moving again, as if I compare sodium and magnesium, what do you get to see? Its size is slightly smaller than it. So that means ionization energy is slightly higher than it. So that means it is metallic, but still it is less metallic as compared to the sodium one, because it will be losing the electron. Definitely it is going to lose the electron, but it will lose the electron with them, that means with the more input of the energy. That means more energy has to be supplied if we compare it with the sodium. So similarly it happens with aluminium, that means ionization energy high, metallic character is decreasing. So again decreasing, and from this onwards size is almost decreasing to a great extent. Chlorine is the smallest one, ionization energy is maximum. So if we want to if we talk of removing an electron from the chlorine, so it won't happen because it is too small in size and ionization energy is too high. So that means it will need an electron. Instead of losing, it will take up an electron, and the element that take up an electron is considered as non-metal. You know, non-metals are electron acceptors, not the donators. So that means it exhibit the maximum non-metallic character. So that means when we are moving down the group, the metallic character is increasing because size is increasing and nuclear charge is decreasing. But when we are moving in the period, then we get to see the size is getting smaller. Smaller means nuclear charge is increasing. When nuclear charge is increasing, that means that it has a tendency to accept an electron rather than losing, it is accepting an electron, and the element which accepts is a non-metal. So along group, metallic character, along period, metallic character decrease and non-metallic increase, and along group the metallic character increase. So that means if we talk of this group, lithium is, though they belong to a metal group, but still lithium is less metallic if we compare it with the cesium, because there is a difference in the ionization energy which occur due to difference in their sizes and the nuclear force of attraction they are experiencing from the nucleus. Right. So this is the property by which we can explain the character. One more thing, if I take an example of non-metallic group, any non-metal group, if I take an example of 14 group, 15 group, 16 group, what we get to see in that? See, as we are moving in these groups, what happened? Obviously the top one element has the smaller size as compared to the rest of the elements, because every time when we move in a group, whether it is metallic group or the group of metalloids or if a group of non-metals, every time a size is increasing as there is an increase in number of shell. I've told you in atomic radii property. So whenever the size is increasing, nuclear charge is decreasing and the ionization energy is decreasing and still the electron affinity is decreasing. So what you get to see, my point is this, what you get to see in a non-metallic group, the upper metal, the upper element is a typical non-metal, but as we move down we know there is an increase in size. So non-metallic property is getting converted to the metalloid property, and as we move more down we get a metal at the bottom. So that means metallic group consists of all metals, and if we talk about non-metallic group, then on the upper side there are non-metals which are getting converted into metalloids. The middle one has property related to the metalloid and the lower one are the typical metals. So that means how I think you have got that how the character varies along group and period. And similarly when we talk about the chemical reactivity, it is the same property by which you can easily correlate. Well, the factor which is responsible for this reactivity is same lies as we did with the metallic and the non-metallic character. The element which has the bigger size means the less ionization energy, it can easily lose an electron, it is more reactive. So reactivity means if whether the atom lose, whether the atom gain, whatever it is doing, it is undergoing a change in its electron in the valence shell that makes it reactive or less reactive. So by considering the energies which are getting liberated from an atom or the energy which you are giving to an atom indicates its reactivity, and it's totally dependent upon the nuclear charge and the atomic size. So this is how we take up these properties. One more property, that is the nature of oxides. So when we talk about the nature of oxides, what do you mean by the nature? Whenever we talk about nature in chemistry, that indicates that the substance is acid, base or amphoteric or neutral. So we have four kinds of nature in chemistry. The nature means, whenever I use the word nature in chemistry, it indicates that whether the substance is acid, base, neutral or it is amphoteric, right? So alkali comes under the categories of base only, because the bases which dissolve in water are called as alkalis. So we are taking into account a property, the nature of oxides, right? So how it varies? The nature of oxides, metal oxides are always basic in nature. They turn blue litmus red. Similarly, mostly the non-metal oxides are acidic in nature. They turn red litmus blue. And there exist few oxides which are amphoteric in nature. That means they have acidic character also and they have basic. I have an example for you. Just keep in mind, it's an important one. So aluminium oxide and zinc oxides are amphoteric in nature. They have acidic as well as basic character. They react with acid also and they react with base also. Like how they react, just to simplify it, I am giving example. It's not in your syllabus, but just to make you know that how it reacts. Suppose I am taking example of Al2O3, I am reacting with acid also, and similarly I am reacting it with base also. So it can react, the both of them, that is a strong acid, hydrochloric acid, this is a strong base, sodium hydroxide. So what happens, it forms AlCl3 with H2O, and here it forms sodium aluminate plus H2O. So that means the reaction can occur with both of them, which shows it is amphoteric in nature. Likewise, we can show it for zinc also. So when we are using zinc oxide, in case of aluminium oxide, it will be forming zinc chloride, and here it will be forming sodium zincate. So that shows they are amphoteric in nature. So our point is not this, I am just telling you to make you more familiar with the concept, but our concept is that how the property nature of oxides vary along group and period. So whenever, now you know that where do we find the metals, where do we find the non-metals, and where are metalloids, you know that. So the elements, the place where the metal occur, the metal oxides are going to be basic, and as the metallic character increase, that means the basic character of oxide is increasing. So as we did that, when we are moving down the group, the metallic character is increasing. That means we know the metal oxide nature is basic. So that means that as we move down the group, the basic nature of metal oxide is increasing. That means when metal oxide dissolve in water, it forms a strong base. So as we are moving down, the basic character is increasing. The bond gets weakened and easily the OH ion gets released. Similarly, when we are talking about the non-metals, we get the non-metals typical on extreme right at the top. So there, that means they are more acidic. As we move down, the non-metallic character is decreasing, metallic is increasing. That means acidic character is changing into amphoteric because you get metalloid and mid, I told you. And below it at the bottom we get metals, so definitely we get to have the basic oxides. So this is how the nature of oxides vary. One more property you should know. What is it? It is not in your syllabus, the elaborate information of that property, but still it is an important property. You get to have certain phenomena which are related to that property. That is the electronegativity. What is it actually? See, we have done bonding also in the previous chapter, so you are familiar with bonding as well. So you remember, I think, the covalent bond. So just take an example of a covalent bond. Suppose I am taking an example of hydrogen molecule. So you did like this now. You remember that what kind of bonding is present in H2, you know how to make it now. So we have the hydrogen atoms linked to each other like as I have shown in the figure. So what happens? These both atoms are similar to each other. All the properties of these hydrogen atoms are similar. So that means their attraction for this shared pair is equal. That means the attraction, the force with which this hydrogen is attracting this shared pair and the force with which this hydrogen is attracting this shared pair is exactly the same. So that means there is an equal force of attraction. What happens? This shared pair lies in the mid. It happens only for the similar atoms. But if I am taking an example of dissimilar atoms like HCl, what do we observe? Again, the bond formed, covalent, single covalent bond, you know that. So the attraction for the shared pair by hydrogen and the attraction for the shared pair by the chlorine is not at all same. I am repeating again, between the similar atoms, the attraction for the shared pair is same. But if there is a bond between dissimilar atoms, the attraction for the shared pair is not same. The one which is smaller in size is attracting the shared pair more toward itself, and the other one which is bigger as compared to the other one is attracting the shared pair with less force of attraction. So out of H and Cl, Cl is smaller. We did that chlorine lies here and hydrogen here. So obviously chlorine is going to be smaller. So that means chlorine is smaller and hydrogen is comparatively bigger. So what will happen? This shared pair doesn't lie in mid. It get displaced little towards the atom which is smaller in size. So that means this shared pair is being attracted by the chlorine atom. It shifts little more towards the chlorine. So what happened as a result? The electron pair has shift towards the chlorine. That means the negative charge which is surrounding the chlorine has just increased up to certain amount. So we say it acquire a partial negative charge. Partial means a small amount of increase in the negative charge. Earlier they both were neutral, but when they are bonded to each other, shared pair get displaced, a little displaced due to smaller size of chlorine. So it gets a partial negative charge because electron density around the chlorine now increases, and compared to hydrogen there is a decrease in electron density. That means it has acquired a partial positive charge. So this shows, this make the covalent bond polar in nature. Otherwise the covalent bond molecules which are bonded to each other by sharing of electron do not have any kind of charges. But you can see in it that in a covalent bond there is a charge, no matter the charge is small or maximum, but still it has a charge. So covalent bond which has a, you can say the charge separation is called as polar covalent bond. So where do this electronegativity come from? Yeah, why I am making you study this whole concept? Because I want you to know what is it, this electronegativity, what is the application where it is being used. So electronegativity is just a tendency to attract shared pair of electron more toward itself. It is a property that an atom is smaller in size, that is why it is attracting the shared pair more toward itself. This is called as electronegativity.